Thank you for the introduction. I'll be describing a zero standby power wake-up circuit for infrared wireless remote control terminals that makes an external mechanical on-off switch unnecessary. By way of background, I'll say a few words about the requirements for a zero standby power wake-up circuit. The main part of my talk concerns a self-powered infrared photosensor switch, which is a key device in the wake-up circuit. The switch consists of an ultra-low power rising edge detector and a noise current canceller. I describe the key features of these two circuits that enable the switch to operate in a self-powered manner even with environmental noise. I'll also describe the characteristics of a self-powered photosensor switch and some of its applications. Here are some battery-operated mobile terminals. They are small and light and have a wireless capability, but we have to turn them on with an external mechanical switch, and that makes them a little inconvenient. The reason for the switch is that if the terminal were put into standby mode so that they could always detect the signal from a wireless mouse or a remote controller, then they would dissipate too much power. Moreover, if you forget to turn off the switch and don't use the terminal for a while, the battery will be drained completely. To make such devices easier to use, we have to get rid of the mechanical switch. One of the best ways to do that is to use an automatic electronic switch with a zero standby power wake-up circuit. In my talk, I explain a self-powered photosensor switch with an infrared LED energy harvester, which is a key device in a zero standby wake-up circuit. Next, I describe a self-powered infrared photosensor switch with an IR LED energy harvester. These graphs show the power generation characteristics of an IR LED energy harvester when it is irradiated with IR light from the remote controller of a commercial TV set. At a distance of 6 meters from the controller, the short circuit current is 0.15 nanoampere and open voltage 0.38 volt. The maximum generated power of 40 picowatts occurs when the open voltage is 0.3 volt. These are the noise current characteristics under fluorescence light in a room. The noise current is 5 times larger than that for the remote controller. If you turn on the remote controller under fluorescent light, the noise current is superimposed on the original current. And if someone walks in front of the energy harvester, the energy harvester performs a switching operation. So, two key circuits are required for self-powered switching and the detection only of pulse signals. One in ultra-low power pulse signal detector that detects the steep edge of a pulse signal and has a picowatt-level power dissipation. The other is a noise current canceller that subtracts the noise current from the total generated current. Next, I'll describe these two circuits. This is a block diagram of a self-powered photosensor switch. The switch consists of one rising edge detector and a noise current canceller. The rising detector is an ultra-low power differential amplifier with an input offset voltage. One of the differential input is connected to VDD, and the other is connected to an RC filter circuit. The amplifier detects the first transition of VDD and dissipates on the order of a picowatt of power because it operates in the sub-threshold voltage region. The noise current canceller suppresses the supply voltage in the deep sub-threshold voltage region that allows the detector to detect the rising edge of the supply voltage. This is the circuit diagram of the rising edge detector. The RC filter circuit extracts the first transition of VDD because the differential between the input voltage of the differential amplifier becomes large. We adjusted the gate length ratio of the two driver MOSFET for the input offset voltage. This is a graph of the difference between the input voltages versus the transition rate of the supply voltage. At a transition rate of 2 volts per second, the difference between the input voltage is 13 millivolts. This value of 2 volts per second is equal to the transition rate of the output voltage of the LED energy harvester due to an IR light pulse from the remote controller. So, we adjusted the gate length ratio of L4 to L3 to suit an amplifier with an offset voltage of 30 millivolts. These curves show the output voltage swing of the amplifier for different gate length ratio of the driver MOSFET. We set the ratio to 0.85 so that the amplifier would output a voltage of 0.28 volt when the transition rate of the supply voltage is this target value. This is a circuit diagram of the noise current canceller. It consists of a voltage detector and a current source composed of the low Vth MOSFET M1, the hold capacitor C1, and the NMOSFET M2, which acts as a switch. When the supply voltage exceeds the operating voltage of the rising edge detector, the voltage detector causes the switch M2 to turn on. Then, the diode connected low voltage NMOSFET subtracts most of the noise current from the total current. The hold capacitor keeps the current to the sink constant when the switch turns off. This graph shows the load current of the diode connected low voltage MOSFET superimposed on the IV characteristics of the LED energy harvester. The supply voltage of the noise current starts at 0.3 volts and converges along this trajectory to the final point at 0.15 volt. These are simulated waveforms of the photosensor switch without environmental noise. For a step response of 0.15 nanoampere in the generated current, the rising edge detector starts to detect the transition when the supply voltage reaches 0.3 volts. On the other hand, for a ramp response with a transition rate of 0.15 nanoampere per second, which corresponds to a supply voltage transition rate of 1 volt per second, the rising edge detector does not detect the transition. These are waveforms of the photosensor switch with environmental noise current of 10 nanoamperes. For a step response, the logic detector again detects the transition because the supply voltage is less than the operating voltage of the detector. Well, on the other hand, for a ramp response, the rising edge circuit does not detect the transition. The final topic is the experiment on the photosensor switch and some applications. To verify the effectiveness of our self-powered photosensor switch, we fabricated this zero standby wake-up circuit on a 0.6 micron CMOS process. It is composed of a self-powered photosensor switch and a CMOS latch circuit. The latch circuit is powered by an external supply voltage and maintains the signal detected by the switch circuit. These graphs show the transient characteristics of the circuit. When the supply voltage has a transition rate of over 2 volts per second, the wake-up circuit detects the transition. This is a photograph of the experimental system we used to measure the response time of the wake-up circuit. The system consists of an IR LED energy transmitter and IR LED energy harvester and the wake-up circuit. When the LED transmitter is driven by a supply voltage of 0.98 volt, the response time for the wake-up circuit is 48 milliseconds. This result is about the same as that for the LED energy harvester at a distance of 6 meters from a commercial remote controller. This is a photograph of a wireless digital photo frame with no external switch. We made it as an application of the zero standby power wake-up circuit. We found that a commercial IR remote controller could wake the device up at a distance of 6 meters and that the standby current was just 0.5 nanoampere. This is another application. This is a wireless remote controller Ludo car. Instead of an external switch, it has our zero standby wake-up circuit built in. When you touch a control button on the remote controller, the car starts up automatically and can be controlled as usual. In summary, we fabricated zero standby wake-up circuit with a self-powered photosensor switch and demonstrated its effectiveness in wireless IR remote control terminals with no external switch. This concludes my presentation. Thank you.